All the batteries or power sources that we've been using so far in all of our circuits have been ideal, meaning that if we say that it's a 12-volt power source, then you actually get 12 volts going to your circuit. But if you're actually dealing with cells, or you might try to call them batteries, that's just not true. They have an EMF, which is your open circuit potential difference. No current is actually flowing, kind of an ideal based upon the chemical reaction of the battery. That they could provide, but they also have some internal resistance, and that internal resistance actually uses up some of that uses up some of that voltage, making your terminal voltage, what's actually able to come out, a little bit less. Whenever we say voltage, please remember V equals change in energy, also known as work, divided by charge here. So in other words, what's happening whenever you have current coming out of a cell, like this one up here, you actually have the current coming from the EMF, chemical potential. We'll draw that as what you might be calling a battery right now. But as it flows around the circuit, whenever it comes out here, it's going to have to pass through the internal resistor. Now, where that internal resistor really represents the amount of energy that is used up in the chemical reaction, because not all of the potential from that chemical reaction is actually available to be able to go out to our circuit, making the terminal voltage, the voltage of the outside part of the cell that then is available to be used in our resistor, terminal voltage, a little bit less than the EMF, what would be the ideal. And if you don't put it in a circuit, if you don't put your cell in the circuit, you just put a multimeter or a voltmeter around the outside, you would measure the terminal voltage. But as soon as current starts flowing, V equals IR, right? The current that flows through that internal resistor is going to use up a little bit of the potential energy. Now, this applies to both primary cells and secondary cells, rechargeable and non-rechargeable. Let's talk for a quick second about electrical power. Now, power is equal to I squared times R, right? Or it's equal to I times V. We have a bunch of different power equations we went over, but I want to emphasize the total power that a cell can provide. I times the internal resistor. We're using little r for resistor, plus, or excuse me, I squared times little r, I squared times big R, the total resistance of the outside of the circuit. In other words, add up the power used in the internal resistor with the power used or dissipated across the load, or the rest of the circuit here. If you actually want to see the power given to the load, or out here, just based upon EMF and resistors, an equation that you do not have to derive, but you may use, is already there for you, given to you from our textbook. There, once again, you don't have to derive. Another interesting relationship that comes from that equation is the spot where you actually get maximum power to your load resistor is when your load resistor, or the outside of the circuit, the resistance of that, equals the internal resistance of the battery. Let's take a look at a few equations dealing with EMF and internal resistance. Now, the equation given to you in your data booklet, base equation here, EMF equals the current flowing around the circuit or flowing out of the battery, times, in parentheses, the combination of the internal resistance, little r, and the equivalent resistance of the circuit, or if there's only one single resistor, which will very often happen in these type of problems for you right now, the resistance of the load, large R. Now, this equation should make a lot of sense, because since there's only two resistors, and even though this resistor is inside the cell, right, it is still in series with the load resistor here, excuse me, coming out this way, positive side of the battery. It doesn't matter which side you put the little resistor inside of a cell, because it's still in series, right? And so current's going to come back through one way or another there. So they're in series, which means that it's V equals I times R here, the combination of those two resistors in series. Now, some more interesting things also begin to happen whenever we distribute that current. Now, in this case, what I should recognize, I times big R is the total voltage used up on the outside of the current, or outside of the cell. That's also known as the terminal voltage, the voltage used up, excuse me, not current, but the voltage used up on the outside of the cell, the terminal voltage. What are we using up out here on this part of our actual circuit there, which would be whatever the terminal voltage is. And then on the inside, I'm going to actually have, this is the voltage used up in the battery itself. there or in the cell itself. Let me change, if I may, the IR into terminal voltage, a very common thing to do. And then I want to solve that around for terminal voltage now. So I'm going to end up having minus IR plus E equals VT. Now, using that equation, this graph over here should make a lot more sense. This is in the form of if I put voltage on the y-axis and I put current on the x-axis and I graph out, maybe I'm increasing the load resistor, so I'm gradually making that resistor there larger and larger and larger in an experiment, just so that I can decrease the current. And so maybe I'm doing experiment, hey, how does the current that flows out of the battery affect the terminal voltage that I would end up having? So I'm measuring terminal voltage. I put terminal voltage on the y-axis. I put current on the x-axis. So as I increase the resistance, thus decreasing the current, what I'd end up finding here is this sort of graph, where if I look at my equation that we have derived here, the slope here's my x value, current, here's my y value. The slope should be the negative internal resistance, and the y-axis should be the EMF. Let's work a couple of example problems now. A cell EMF of 12 volts, internal resistance 1.5 ohms, connected in series 20 ohm load resistor. Determine three things: the current in the circuit, the terminal voltage, and the power dissipated in the resistor. And here we're referring to the 20 ohm resistor, the external circuit. In this case, I can just simply use my base EMF equation. E equals I, R plus R. So here you see a substitute, and truthfully, before I even got started, I should have done a variable bank. A variable bank is going to end up highlighting exactly what I need to use here. So actually filling out, hey, I know E, I know R, I know R, I know I, that substitutes in perfectly into my base equation, and now it's just basic algebra. I'm going to have 21.5 and divide that over. That leaves me 0.558 amps with three significant figures. Now, that's an interesting thing because generally we would have rounded to two significant figures because my internal resistance only was reported to two significant figures. But if we did this properly, we notice this is addition and subtraction. Whenever we are adding, subtracting, significant figure rule simply says you're only as strong as your least precise measurement for addition and subtraction. So both of these go down to the tenths place, meaning that I should go down to the tenths place on that addition. Now, whenever I do multiplication division rule, because I'm dividing the 21.5 over, and I round to least number of significant figures, 3, 3, meaning that I should have 3 here in this case. All right, so now let's actually solve for our terminal voltage, the next thing that we need to go after. Now that I know the current, and I know the external resistance, the resistance of the load, I can just simply do V equals IR. Terminal voltage equals the current times the resistance of the load. And end up with 11.2 volts. So obviously 0.8 volts is actually being used up inside the cell. Now, if I want to actually see the power delivered to the load, now there's a couple of different ways we could do this. We could have used that nice power equation that we had all the way at the beginning of this video, but now that I've solved all the way through here, I actually don't need that. I can just simply use the base power equation. Power equals V times I. And I end up with a power dissipated in the load of 6.23 watts. Of course, I could have used the equation P equals I squared R, or P equals V squared over R there, because I knew VI and R for the load at that point in time. In solving these problems, sometimes, especially if you're asked for all three things, the current, terminal voltage, and power dissipated, it is easiest to solve your base equation to get current and then let that flow into all of the other things. If you're asked more directly for terminal voltage, on the previous slide, we actually solved an equation around for terminal voltage. We use that to explain the graph. Maybe you want to jump to that equation. If you were only asked for power dissipated in the load resistor, maybe then instead of having to chain all the way through, you do want to jump to the little bit longer equation you found on the very first slide of this video. Last example problem. In this case, we're actually solving for the EMF and the internal resistance of the battery. This might be a case where you do not have a voltmeter. You only have an amp meter. How would you figure out things about a battery if you only had an amp meter here. Obviously, if you had a voltmeter, then you could just simply not connect the battery into a circuit and measure the voltage across the battery. That would give you the EMF. Then connect it into a circuit with a known resistance. See the current that flows. You can measure the terminal voltage at that point in time, and then life would be pretty easy because then you could actually use your terminal voltage equation that we talked about in comparison against the graph. But without one, it becomes a little bit more complicated. So let's imagine we connected two different resistors in this case. First, we connect a 9 ohm resistor, and we find that 350 milliamps flows through the circuit. And then whenever we half that resistance, 4.5, we get 500 milliamps through it. It's not exactly a doubling thing, which maybe you thought would end up happening here, but it's not, because the internal resistor is going to end up using a little bit more at that point in time because the internal resistor did not change. We're going to calculate the EMF and the internal resistance of the battery. Now let's make a equation bank for each circuit. Now, after making my equation bank for both circuits, what I can see is that the EMF and the internal resistance is the same in both because it's the same battery. I didn't change out the battery, and so I can already sense a system of equations coming on here. So we're going to substitute in this case, into our base equation for EMF. EMF equals I, resistance load, plus the internal resistance load into both, and then we'll have a system of equations to solve via substitution. Now, in this case, instead of running this system of equations via substitution, which is the most common method you'll end up using in your physics class, obviously, let's actually set them equal to each other. Notice that I already have the EMF solved for on both of them. That's just how the equation is built. So all I have to do is set them equal to each other, and that automatically cancels out a variable. All right, so now all I need to do is distribute in for both of these. I'll collect like terms and solve for my internal resistance. And that leaves me all the way with 6.0 ohms, 2 sig figs because of my resistance here, 4.5, 9.0, 2 sig figs. And the very first mathematical operation I did was multiplication. All right, now that we have the internal resistance, let's take that internal resistance and let's substitute it back in on one of our equations to find the EMF. That allows me to calculate the EMF to 5.25 volts using my proper significant figures here. That should be 5.3 volts right there. So that's how you can end up calculating if you need a system of equations, which does come up rather often whenever you're solving these type of problems with internal resistance. Now, these internal resistance problems can actually be chained into all other types of problems that you've used before. Don't get freaked out by that. Anytime you have an internal resistance, just treat it as part of the circuit. It's just a resistor. Even though it is technically inside the cell, it doesn't matter if it's inside the cell or if you treat it a little bit outside the cell as just a resistor that would be in series with that battery.